Welcome to the video lecture for section 5.3, determining inverses using composition of functions. As we saw in the previous two sections, we can use composition of functions to run an input through one function and then run the result through another. And back in 5.1, we saw that an inverse function undoes whatever a function, a one-to-one function, originally did. So let's assume the existence of the function f. This is just a generic function. We don't have any specific formula for it. And we're going to assume that it's a one-to-one function, so we're talking about any one-to-one function at all. That means that we can also talk about its inverse function. So I really like to go back when we're talking about inverses and functions and one-to-one and all of that stuff in this chapter, and remember that we're just thinking of functions as taking in an input. So if we take x and plug that into a function, say f, this mysterious machine, we don't know what it does, but it takes an input and it turns it into an output. Okay, and remember this output can also be called f of x. Alright, now since this function is one-to-one, if we take that output and we run it back through our inverse function, another mysterious formula, machine turns it back into the original input. So this is kind of a nice way of thinking of it. We take our input, plug it in, get an output, and then we take that output, plug it into the inverse function. The inverse undoes whatever the original function did, and we get back where we started. Now this is sort of cumbersome notation. We wouldn't want to have to write this big diagram every time we talked about a function. And so our notation, we could say our inverse function is the function acting last. So it's taking the input of f of x, and it's giving us back the output of x. So remember that this function within a function notation can be written as f inverse composed with f. Right? The outer function comes first, the inner function comes second, and this action, this pattern going from x to y and then back to x again, should work for all x in the domain of the function that we plug x into, which is f. Alright. So that's a nice way to see if two functions are inverses. If you can plug something into the first function and then plug the result into the second function and get back where you started, no matter what you start with, then there's a good chance that we're talking about inverses. Now, if f inverse is the inverse of the function f, then that relationship should go the other way. F is, by definition, the inverse of f inverse, and that's a little weird to think about. But if f inverse undoes f, then f should also undo f inverse. So if we think of plugging an x value into the inverse function, which is a perfectly valid function, we could come across it and not necessarily know that it's an inverse function. It'll just be called g, maybe. If we do that, we'll get an output, y, or we would probably prefer to call it f inverse of x, whatever that x value is. Okay, now if we take that y value and plug that back into the function f, since f is f inverse's inverse, we should get back where we started. So again, we see this pattern of f undoing what f inverse did. Okay, so the function to act last here is f, so f of f inverse of x gives us an output of x. Okay, so plugging something into F inverse and then the result into F should get us back to whatever we started with. And notationally, we would denote this expression, plugging F inverse into F, as F composed with F inverse of x. Parentheses got a little crumbly there. Let's rewrite that. Alright. Now, this should work if these really are inverses for any x in the domain of the function that we plug x's into, in this case, F inverse. Okay. So these two bullet points are our test. What we need to do, if we have two functions and we think that they're inverses, we need to see what we get when we compose one function with the other and the other with the one. So if you refer to the notes, you'll see a similar argument sort of explained to what we saw here. But the only theorem in this section that matters at all is theorem 5.3, which says that if you have two functions f and g, then they're inverses if and only if f composed with g of x gives you x, and g composed with f of x gives you x for every x in the domain of the inner function. So the domain of g here in the first case, the first function we plug stuff into, and for every x in the domain of f here in the second case, since we're plugging x into f and then the result into g. Okay, so that is our test in this section, and that's how we're going to verify that two functions are inverses of each other, or potentially discover that two functions are not inverses of each other. So in the past, we usually see how to solve a problem and then how to check our work. This is how we check our work. When we, for instance, determine the inverse of a function, we want to make sure we got it right. We're going to do this process to verify. So here we see our first example. We're going to verify that f and g are inverses of each other if f is this first function here, 3x minus 1, and g is this second function, x plus 1 over 3. So our test, referring to theorem 5.3, we're first going to evaluate f composed with g of x. Okay? And we'll simplify it as much as we can. Ultimately, we hope that this is equal to x. Alright, so let's get started. F composed with g, that means we're going to plug g into f. Okay, well, g is this expression, x plus 1 over 3. So that's what we're plugging into f. And what's that going to look like? Well, if we plug x plus 1 over 3 in, we're plugging it in everywhere we have an x in the definition of f. So f takes 3 times the input and subtracts 1. So technically we are almost done with this. We've evaluated f composed with g of x. We have the function, now we just need to simplify it and see what it really turns out to be. Well, if I multiply 3 times the third, those are going to cancel, and we just get x plus 1 from the parentheses minus 1 left over, and our plus 1 and our minus 1 cancel, and we're left with x. Now, every step that we took is valid for any value of x, right? This does not depend on what x is to cancel 3 and a third, or to cancel the plus 1 and the minus 1. So I would say for all x, and that part's important. We'll see later on that sometimes the steps that we take to simplify don't always hold. They may be contingent on the value that x takes. Okay, now we're not quite done. These are only inverses of each other if this works going both ways. So now let's evaluate g composed with f of x, and this time this means we're going to plug f into g, so g is our outer function, and we'll plug f into it, so now we're going to plug 3x minus 1 into g. And what does g do? Well, we're going to put 3x minus 1 plus 1 over 3. So we're replacing this x in g with 3x minus 1. Alright, well those parentheses are a little silly. We don't really need those. This is 3x minus 1 plus 1 over 3. And the first thing I notice is minus 1 and plus 1 cancel, and we're left with 3x over over 3. Spoke. Now 3 divided by 3, those cancel each other. They're common factors, and we're just left with x. And again, every step that we took was independent of what x was. These are always valid steps. Negative 1 plus 1 is a net 0, so those cancel. 3 over 3 cancels and gives us a factor of 1, so we're just left with x. So, going both directions, we get the punchline that we want. So we can say that these are inverses by Theorem 5.3. Okay, so that's a taste for the process that we need to use in this section, checking our work. Let's take a look at another. Actually, before I move on, I do want to talk very quickly about notation. So as soon as we figure out that these two functions are inverses, if we were to write it out, we would say f is the inverse of g. So we could say that f equals g inverse, right? F is the inverse of g. Or we could think of it the other way and say that g is the inverse of f. Maybe f is our more interesting function, or the one that we care more about for some reason. And then we might want to use the notation that g equals f inverse. So we may want to drop g and talk about f and f inverse. Alright, so that's kind of a nice shorthand for our conclusion. We can say these are inverses of each other, or we could say that f is g inverse, or that g is f inverse. Does not particularly matter which one you highlight as your main function, and which one you highlight as its inverse. Alright, so let's take a look at a situation where these functions are not inverses. So here we have f being x squared plus 1 and g being the square root of x minus 1. So let's look at this first as f composed with g of x. Let's figure out what that function is. Well, f composed with g means we're going to take g and plug it into f. So what does that entail? Well, we're going to take all of g and plug that into our function f. Okay, so what are we doing with our inputs? Well, f takes the input and squares it and adds 1. So we'll take g, the square root of x minus 1, we'll square it and we'll add 1. So I've got my input here in parentheses, my input being the whole function g of x. Alright, well now what I have here is a binomial expression, square root of x minus 1. Now this is not equal to x minus 1 squared. The square means that we need to FOIL. Alright, now if we FOIL, we would get the square root of x times the square root of x, which gives us x. Outside would be minus the square root of x. Inside would be the same. And negative 1 times negative 1, the last term would be plus 1. Okay, so that's the whole binomial squared. And we also need to add the 1 left over. So if we simplify this, we get x minus 2 square root of x plus 2. And I think that's about as simple as this is going to get, and I think you'll agree that this is not generally equal to x. So if this does not simplify down to x, or if that equality is dependent on x, if this is not an identity, in other words, then we say these are not inverses. Again, by theorem 5.3. Alright, so we're using a lot of logic in this section. We're basing our conclusions for every problem that we look at on the reasoning, on the logic of theorem 5.3. So make sure you read that over, really digest it, and understand what's going on with the function and its inverse to help you along. Alright, now so far we've proven that functions are inverses of each other, or proven that they are not inverses of each other, but what if we just don't know? Well, one way to determine whether functions are inverses is to take one of them, find its inverse, and see if it matches the other function you've been given. But that's not a really great way to check your work. Say you came up with this function g here, and you think it's the inverse of your function f. Well, we want to check. So let's evaluate and simplify the composition functions, f composed with g of x, and later on we'll evaluate g composed with f of x. So for right now, f composed with g is plugging the second function g into the first function f. Now that does kind of confuse the matter of which function we're plugging stuff into. Our inner function is g of x, our outer function is f, so we work from the inside out, so we're plugging our inputs into g and then plugging the result into f. So the function g of x is defined here to be 7x minus 2. So that's what we're going to plug into the function f. So what would that look like? Well, f takes the input, 7x minus 2, and divides it by 7, and then adds 2. So here we've got our input. Normally we would plug in a number, or think of that as x, but we're plugging in this whole function, g of x. Alright. So if I wanted to simplify this, one way that I might do that would be to think of 7x minus 2 over 7 as 7x over 7 minus 2 over 7. So this section is going to really quiz you on your familiarity and comfort with fractions, and you want to make sure that you're current on all of the reasoning and rules behind how we manipulate fractions. Alright, so that is our first term, and we're adding 2. Well, 7 over 7 cancels, and we just get x minus 2 over 7 us 2 left over. Okay, well, for one thing, 2 could be written as 14/7 if we wanted a common denominator, so we could combine those constants. So negative 2/7 plus 14/7 would give us positive 12/7. Okay, so f composed with g of x is x plus 12/7. Well, x plus 12/7 is certainly not equal to x. So, we're done. These are not inverses. Notice that my logic, going back to that theorem, the composition function has to equal x going in both directions. So if we look at one direction, if we look at f composed with g and we don't get x, then we can quit, because it doesn't matter what happens going the other way. It has to work both directions. Okay, so these are not inverses of each other. We did something wrong, or just we're given two functions that were not inverses. Alright, let's look at one more of this type of problem. Determine if two functions are inverses. So, we'll look first at f composed with g of x. That means we're going to plug g into f. Now I'll start going a little more quickly. We're going to plug all of g, x cubed plus 1, into f. In other words, we're going to replace x with x cubed plus 1. So the outer structure will be the cube root, and we'll subtract 1. The inner structure, x cubed plus 1. Fantastic. So the better you get with those composition type problems, the quicker this process will go. So f composed with g, if we simplify a little, we really don't need those parentheses. This is the cube root of x cubed plus 1 minus 1. Well, that cancels and we get 0 there. So this is really the cube root of x cubed. And generally speaking, the cube root of a number cubed is x, whatever that number was, right? If we take 2 and we cube it, we get 8. Cube root it, we'll get back to 2. If you take negative, say, 5, cube it first, working from the inside out, would get negative 125. Its cube root brings us back to negative 5. Okay, so this works for all x. Punchline here, f composed with g is equal to x. Now let's look at the other direction. Well, g composed with f is going to involve plugging f, in other words the cube root of x minus 1, into g. So we're going to take the cube root of x minus 1. That's our input. We're going to cube it and subtract 1. Well, we very quickly see, remember, if you cube anything under a cube root, the cube root and the cube are going to cancel. And we will get what's inside, x minus 1, plus the 1 left over from the outside of the expression, from g of x. And again, minus 1 and plus 1 cancel, leaving us with x. And again, every step that we took is valid regardless of the value of x. So that conclusion, both of those ideas together, shows that these are inverses. So f is g inverse, or if you prefer, g is f inverse. In other words, they are inverses of each other. And by they I mean f and g. Alright, so we're finished with that one. These worked out. We got x for every value of x in the domain of either function, right? Okay, well, we're going to look at one more of these, one which is a little bit more subtle. Okay, so here we've got two more functions, f of x equals x squared, and g of x equals the square root of x, and we're going to see if these are inverses of each other. Well, naively we might assume, well, x squared squares numbers, square root of x square roots numbers, and these seem like inverse operations of each other. They seem to undo each other. But let's look at f and g. Okay, f of x equals x squared has a domain of all real numbers, right? Any real number can be squared. But on the other hand, g of x, the square root function, remember we never want to square root a negative, so its domain is 0 to infinity. Now I'm mentioning these now because the really important part of Theorem 5.3 is that for all x in the domain of whichever function part. So let's look at f composed with g first. Okay, so what are we going to do? We're going to plug g into f first. In other words, we're going to take the square root of x, that's going to be our input, and we'll square it. Now, it is always true that something under square root, when we square it, we get whatever's inside. So this is true for all x, for any real number. In particular, it's true for any x in the non-negative real numbers. Okay, so that direction worked. We got x for all x in the domain of the inner function, in this case g. Let's look at the other direction now. Well, g composed with f, we're going to go the other way. We're going to take x squared and we're going to plug that into g. Okay, so x squared is going to be our input, and what are we plugging it into? Well, we're square rooting. Now, one very subtle little issue with the order of these, if we take a number, say -3, and we square it, we get 9, right? So if our input is x equals -3, we'll square it first, we'll get 9, and then the square root of that would be 3, not -3. It turns out, and you may have seen this before, but the square root of x squared is actually the absolute value of x. So this is not generally equal to x. In other words, it's not equal to x for any x we might plug in. I should say any arbitrary x. It's true for a lot of x values. This is equal to x, for instance, if x is 0 or greater. So this is only equal to x when x is greater than or equal to 0, not for any possible x in that domain of the inner function, this time negative infinity to infinity. Now, mathematicians like to use the word any interchangeably with the word all. So there are x values for which this is not true. Let's take a look at that. For example, if it works, or if it does not work for one x value, then these are not inverses. Okay, so we're going to take x equals -3. F of -3 equals -3 squared, which is equal to 9. So if we plug that back in, so we'll take that output and plug it into our supposed inverse function and see what g has to say. So if we plug 9 into g takes the square root of our input and gives us back 3. This is not equal to our original input, so we cannot get back to where we started. And that's the problem with the relationship between these two functions. So these are not inverses for the entire domain of f, right? There's stuff that we can plug into f that we can't ever get back to. But if we restrict the domain of f to be 0 to infinity, in other words, if we chop off part of the function's domain, then there is no issue. Right? Any positive number that we plug into f can be returned when we plug the result back into g. So these are inverses most of the time. These are inverses over most of the domain of f, just not the whole domain, which means that as they were given at the very beginning, they are not. So it's a very subtle question. Now, thinking about what it means for a function to have an inverse, we could have identified that there was going to be trouble right away when we think of f of x. That function is not one-to-one. So asking if some other function is its inverse, we should be able to immediately say, probably not, because this function doesn't have an inverse function. So you can, if you're on your toes and you remember all of these little details about inverses and one-to-one functions and all of that stuff back from 5.1, you can kind of get around some of the trickier nuances introduced in this section. So that is about as interesting as this is going to get, and those are all the tools that you'll need to get started on the homework problems. Do go ahead and make a start on those and bring any questions that you have to class.